Hello, this video is entitled Percolation and Porous Media. What I'm going to do first is describe a mathematical process, physical process called percolation, and then I'm going to show how that applies to flow and porous media. So what I've shown behind me is a grid. You could imagine that it's a layout of matchsticks, for instance, or electrical conductors. It's also, of course, going to describe a porous medium. But let's just think about it as a grid. And what percolation is a random process. So I've got some yellow chalk, and what I'm going to do at random is simply fill in one of the links. Exactly what do I mean here? What I mean is, here, I'm going to just choose at random a link, and I'm going to colour it in yellow. That's all I'm going to do. Right? I can imagine throwing a dice or having a random number generator that would simply at random make yellow one of these links. And the way in which you could think about it is, imagine I've got a voltage across here and these links are electrical conductors to begin, and where I haven't coloured it in, it doesn't conduct electricity. So you can imagine, yes, to begin with, there's no current because I've just got one conductor here, but the grid isn't connected. So it's random. Okay, so the next one, I can do the vertical ones as well. I do this at random. I keep doing this at random. Okay, and we can do this, and it will take some time, but that's the whole beauty of it. And we can have something connected here, we can have something here, and so on and so forth. And as we do this, we can define what's called a probability, P. Okay. So we can define a little p. And what is p? P is simply the fraction of the grid that I've coloured in yellow. Okay, so I can keep doing this, and p continues to increase. And sometimes I might do something that connects this together, and so on and so forth. And as I continue to do this process, I think you can imagine, right, eventually I'm going to fill the entire grid. Okay, so everything's going to be connected. But there's a critical point, okay, which is called here the percolation threshold. So the percolation threshold is defined by PC, and it's the critical fraction of these links, or bonds, as I could call them, okay, the critical fraction of these bonds that I have to fill for there to be a connected path across this lattice. Okay, so if I keep filling, I will eventually reach this critical threshold. And in this particular example, this critical threshold is in fact 1/2. Now, it's not exactly 1/2. You might say, well, it depends exactly how I do it. I might connect sooner than that, if I'm lucky, or maybe unlucky. In an infinite size network, right, everything's going to average out, and that percolation threshold will be 1/2. If it's a finite size network, that percolation threshold may be slightly different, but we want to extrapolate to large systems. So we can imagine in this specific case, we have a case where at a threshold of 1/2, when I've filled in 1/2 of these links, I will finally get a connected network, and I can show it here, a connected network that spans the system. Okay. So in this particular example, I can emphasize the specific path that enables me to connect from one side to the other in red. So in this example here, there's a connected cluster spans across the system. It can even have loops, it can have deviations, but there is a path that goes from left to right. Okay, so that's shown in red. The other parts that can also be filled, remember I should on average have filled about 1/2 of these links, they don't necessarily connect to this connected cluster. right? You can have some wide deviations here. You can see this is the connected cluster up here, but it doesn't connect to the other regions, okay? So that's percolation. So percolation you see in lots of examples. You can imagine, you know, just having a lattice of matchsticks. You can imagine having a lattice here of electrical conductors, you know, and as I either put them in or take them out, when does it first conduct electricity and when does it first not? Okay, so that's percolation. But the reason why I'm interested in percolation, or why we're talking about it in this video, is we want to understand flow in porous media. Now let's take an example, which is called primary drainage. And this is where I have my rock and it's entirely full of water. Okay, it's entirely full of water. So you can imagine this lattice being full of water. And then what I'm going to do is I'm going to inject oil as a non-wetting phase to displace the water. How does that process proceed? Well, the way we think conceptually of a rock, and in other videos you've seen these complex three-dimensional images of the rock, is you can imagine the rock as being composed topologically of wide spaces in the void, okay, and there is called pores, connected to other wide spaces via restrictions. And we call the wide spaces a pore, and the restrictions we call a throat. So this lattice here could represent where on this side I'm injecting oil, okay, and on the other side, so the oil is moving in here, the oil's coming in from the left, okay, so you can see this there. The oil's coming in from the left, and I'm displacing water from the right. Okay. Now, if I do this, if it's the non-wetting phase, the non-wetting phase doesn't like the solid surface. It moves in through the widest regions of the pore space. Okay. So if it goes through the widest regions of the pore space, what's going to happen here is that the oil first will fill all the wide pores at the inlet because it likes filling the pores. So the way in which we conceptualize this is we conceptualize where these links come together. There's a wide region of the pore space. And then these links, these bonds, okay, are the throats. They're the narrower regions that you go through to get into another wide region. You can imagine wandering around a house. The rooms are the wide regions, the pores. To get to another room, you have to go through a restriction. That's the door, okay? So this represents a pore, a wide region. The links represent the throats. And because it's the non-wetting phase that likes to be away from any of the walls, okay, it's restricted by going through the narrow parts of the pore space, okay, those throats. So how you can view what's called a primary drainage process, where oil, a non-wetting phase, displaces water conceptually, okay, just sort of in our heads on a board. Don't get worried, it's really complex pore space, and there must be lots of other things going on. Yes, there are, but conceptually, all that happens is the oil simply fills the widest region of the pore space it can find. And it will fill the pores easily because they are wide, and it's going to be held back by the throats. So in this diagram, what throat is it going to fill first? It's going to fill the widest throat here. It doesn't like the narrow one, so it will fill the widest. That's the easiest for it to fill. So we can now consider a process where what happens is the oil fills here the widest throat, okay? Then it will fill the pore, that's easy, okay? And then now it will fill any of these regions, okay? And here, that's widest. Maybe it's this one now. Then it fills that pore. Okay. And what's the next widest? Well, maybe it's this one. Okay. Now you might say, just a moment, you've already filled in a pathway in red, and now you're using red again. What's going on? What's going on is that this can be described as a type of percolation process. If we imagine that the pores and throats here on this lattice are of different size, but their size is distributed essentially randomly. So we know that a porous medium is highly heterogeneous at the pore size. They have pores of different size, but imagine they're just at random. So rather than us saying, well, we just fill at random, we're filling in order of size, but where those are in space is randomly distributed, it's essentially saying the same thing. So we can view a displacement process in a porous medium as going from wide pore to another wide pore through a restriction, which we call a throat. And when we're injecting the oil, it simply goes through the widest restriction that's available for it. So it doesn't immediately fill here. Imagine that's the next widest restriction. Well, it can't fill here because it's been injected from here. It can't magically zoom or itself, beam itself into the middle of the porous medium. It has to be connected. Okay. So what we find is we find a process where it's equivalent to what I've just shown. The oil is filling the areas I've already shown in red. It will also fill anything that's connected to the inlet that filled, but there may be only a few places here. So it follows this path. Okay, and it can go over here and over here. And each time it's also filling all the pores because these are wider regions, so it's always easier to fill the pores. So you can imagine a progression like this. And just as I've shown, there comes a point at which the oil will have spanned the system. It will have gone from the left to the right. Now, in fluid flow, that's important because at this point, there is a pathway for the oil to flow across the rock. Okay, so it can flow across the rock, and now we can have oil flow as well as water flow because water's filling everything else. But this is not a percolation, a strict normal percolation process, because I haven't filled any of these regions. So actually, I haven't filled half of the throats. It turns out, and this is a subtlety which I don't want to dwell on in this video, turns out that in an infinite system, this is actually an infinitesimal fraction of the pore space. So the oil basically takes a path where it's always going through the widest possible regions. So the way in which you can think about it is, imagine you sort of blow up a big balloon and you try and move it around a building. It's going to be constrained by the doorways, right? The narrow region, and it keeps going through those doorways until you get into the widest pieces of the pore space, okay? So this is basically how the non-wetting phase moves to go all the way through the porous medium. Okay, it spans the porous medium. Okay, so this process is called invasion percolation. So invasion percolation is what happens when I inject oil to displace water in a porous medium. It's not a normal percolation concept, which is just random. So I just do random filling, everywhere. The oil can't do that. It can only fill where it's connected to the inlet. So what this is where the oil simply fills the widest regions of the pore space to which it is connected. Okay, so at each point, it will fill the largest throat where it has a pathway connected to the inlet. So it's an invasion percolation. It actually follows the same path as an ordinary percolation process, but it doesn't fill the regions that are outside the connected cluster. As I continue the displacement, if I continue to inject oil, obviously we'll fill more and more of the pore space. So this is where it first connects, this is the critical point. But as I inject further, I can start filling other regions. I can get the oil better connected. There may be more paths through the network. So an invasion percolation process is simply filling in order of size, but where we have to be connected to the inlet, as opposed to ordinary percolation, where I fill everywhere. The last point about percolation is now I've got a blue chalk. What happens now when I re-inject water? So now I've got oil in my pore space and I want to inject water. The interesting thing here is that if we keep having a water-wet porous medium, so now the water, not like the oil wants to be in the big regions, the water wants to be in the narrow regions. The other thing is, as described in previous videos, the water is in the corners of the pore space. It's always connected in the corners, in the roughness, in the nooks and crannies of the pore space. So if I now inject water here, right, imagine I'm injecting it from the right, the water can in fact flow everywhere through the porous medium. Okay, so what does the water do? The water actually can follow an ordinary percolation process, a normal percolation process. It simply finds the narrowest regions of the pore space, which is say here, and the water can fill anywhere because the water can flow in the corners of the pore space. So when we're considering water flooding, the water going back into the porous medium, that's an ordinary percolation process. The water basically just fills throughout the pore space wherever it can. So there is how percolation theory relates to flow in porous medium. And now I'll make the final comment, which is in order to introduce this idea, and I'm just introducing it in this video. I'm not going through any of the details of percolation theory. There's a very rich theory in physics, can tell you a lot about the behavior, and just introducing it as a concept. But key to the introduction of percolation theory is this conceptualization of a porous medium. And the conceptualization of a porous medium is as follows, that we have wide regions, the pores, that are connected to other wide regions through a restriction that we call a throat. And it's not just as a way of applying percolation theory, because people will say, okay, well, it's an approximate theory with some sort of threshold and lots of physics stuff, but it doesn't do the real thing. It's much more complex. But actually, it can be much richer than that in terms of a description. So the idea here is we're introducing a topological description of the pore space. We have what's called pores and throats. And the concept is as follows. If I have, and I'm drawing it in 2 dimensions, but actually, as you're aware, this is a 3-dimensional network. So a real rock is 3-dimensional. I can only draw in 2 dimensions. Okay. So imagine, as an example, here's an image of the pore space, and what I've shown here shaded is the solid. So this is the void space. So how actually precisely do we conceptualize this? Because it's all very well, pores and throats. Sounds a bit vague, but actually we can do this very precisely, and we can define what's called a pore network. So how is that done? Well, how it's done as follows. You can take any point in the void space here, say, and you can draw a sphere, okay? And you can start with a little sphere. Obviously in 2D it's a circle, okay? And that circle or sphere can get bigger and bigger until it hits the solid. So in this point, there'll be a place that hits the solid like that, okay? Maybe I haven't drawn it that way. Imagine like that, okay? So it first hits the solid here. You can draw spheres for any point in the pore space, okay? And you can define essentially a distance, which is the closest distance to the solid. A pore is defined as having a center where you draw the largest sphere that can fit in the pore space. So where there's the largest sphere, right, this is the center of that sphere is the pore center, okay? So that's the center of a pore. Any other place surrounding it will have a smaller sphere. But what you find is that these spheres can get smaller and smaller and smaller and then start getting bigger and bigger and bigger again. So you can have another pore here where locally it's the biggest sphere, and any other point around it, these spheres get smaller, right? Here it's the biggest sphere. If I choose a neighboring point, all the spheres are smaller, okay? So this is a maximum, essentially, if we consider this distance to the nearest solid, D, and you imagine a three-dimensional map of the D values, a pore is at a maximum. D is a maximum. You go in any direction and D is smaller. But what you find is obviously D gets smaller and smaller and smaller and then starts to get bigger and bigger and bigger again. So you can define a point at which you go from smaller and smaller spheres to bigger and bigger ones. And in fact, what you can do is you can find the largest sphere, okay, that you can fit. So you get a chain of the largest spheres. You can always have smaller spheres that are next to the solid, but there's always going to be a largest sphere sort of in the middle of the pore space. This chain of largest spheres goes from big to small to big again. And where it reaches the minimum, you have what's called a throat. And you can actually define a throat surface. A throat isn't really a sphere. A throat, the restriction, is a surface. And on one side of the surface, the distance maps, the balls get bigger to one pore. And on the other side of this surface, they get bigger, there's a distance map, to another pore. So modern pore networks are a topological description of the pore space. They can be derived from having a three-dimensional image. And they're pores whose center is the center of the wide region. You can associate any voxel between throats as being associated with the pore. A throat is actually technically a surface, a bounding surface between two pore regions. When you have that topological description, you can then apply percolation theory. Percolation theory is normally associated with when these throats fill, because it's the restriction, it's what inhibits the filling. If it's a drainage process, the non-wetting phase is going in. If the wetting phase is going in, this is where filling is favorable, and actually the inhibition to filling is in the pores, okay? And those pores are actually in percolation parlance called sites. So we can describe even the most complex porous medium by a topological representation of pores and throats. And that's very powerful when it comes to describing what's going on. But we can go one step further. We often actually have a pore network model that takes this topological description and then uses it to predict a displacement sequence. Now, sometimes that's considered a bit controversial in this field because people say, oh, it's a simplification. It would be much more accurate to describe the rock in more detail. But actually, this topological description has everything you need to describe capillary controlled displacement. And what's more, it isn't just a ball and stick, sort of lattice. The lattice is irregular, right? Because the pore space is irregular. And associated with the pore and throat, I can associate whatever I like. I can give, for this throat, there will be a critical capillary pressure for filling. With this pore, there'll be a volume. If I'm interested in other processes, I can give it a shape to describe how much wetting phase, say, is in the corners. If I'm interested in interfacial area, I can say it's interfacial area. If I'm interested in chemical reaction, I can have some effective reaction coefficient or an effective area for reaction. I can assign to any pore and throat whatever information I need. It doesn't have to be a simplification. Furthermore, when we're interested in transport, it's the simplification we need. To solve all the flow processes directly in an image that may contain billions and billions of voxels is something that is pushing the envelope of high performance computing. Fair enough. But we can't really elegantly and quickly describe flow processes this way. The analogy would be, if you want to get around London by public transport, use the famous London Underground map, the tube map. The tube map is a topological description of the tunnels underground. They show the links, which are the lines, right? The throats, right? The tunnels. The wider regions are the stations, and they show the connectivity of the stations and the lines. Just as it's important in fluid flow, it's important for transport. That tube map, you can imagine an interactive map on the internet, which has more information. I say, oh, that's just simple. It just shows a line and a station. What use is that? Well, a lot of use, actually. But it could have other information, couldn't it? You could click on the station. It could tell you the timetable of the trains, when the next train is going to arrive. It could even tell you what's around the station, local attractions, where's the nearest restaurant, things like that. So it's a simplification. You might say, well, no, I'd rather have a three-dimensional Google Maps. Something which gives me a three-dimensional representation of all the tunnels underneath London. That's more accurate. So if I want to travel around London, I want that accurate representation. You think that's useless, right? Okay, you've got lots of information. Imagine you even had this map, because it doesn't exist, with an accurate image of all the tunnels underneath London. Fascinating, but totally useless if you want to get around the city. You'd use the tube map, wouldn't you? Because it's a representation, it's a simplification, of course, but it's a simplification that gives you the essence of fluid flow. So without going through the details, the points here to finish this video is percolation is a very powerful concept in mathematical physics, and it's something that can be applied to porous media to describe displacement processes. Furthermore, in that description, and it can be a quantitative predictive description of displacement and fluid properties, macroscopic flow properties, is this idea of a pore network and a pore network model, where we have wide pore spaces connected to other wide pore spaces via restrictions that we call throats. And in percolation parlance, the throats are bonds. They're the ones that get filled in a specific sequence, and the wide regions are the pores, and they're the sites. And then we can have two types of percolation process: invasion percolation in a drainage process, where you fill the largest available throat, but you have to have a connected path all the way to the inlet, and an ordinary percolation process where we essentially fill at random, but that's only possible if we have the wetting phase in the corners of the pore space. Okay, well, I'll end there. Thank you very much.